A água é um dos recursos mais valiosos do planeta. No campo, nas cidades e nas florestas, na agricultura, na indústria, na geração de energia e no lazer. Ela é fundamental em todos os momentos das nossas vidas. Mas a água não está sempre disponível na quantidade e na qualidade que precisamos. No Brasil, temos longos períodos de seca, enchentes frequentes e forte demanda pelo uso da água em regiões com pouca oferta. Para enfrentar esses desafios, foi criada a Agência Nacional de Águas, a autoridade do governo federal responsável por monitorar, planejar e regular o acesso e o uso das águas gerenciadas pela União. A ANA estimula a gestão participativa, que envolve o poder público e representantes dos usuários e da comunidade. Afinal, cuidar de um bem precioso como a água é uma missão da ANA e também de todos nós. Saiba mais sobre a ANA no site www.ana.gov.br.
Com apenas 8% da rede bancária na região, o Banco do Nordeste concentra quase 65% do total de financiamentos de crédito de longo e curto prazos em todos os setores da economia. O Banco do Nordeste é também o principal agente financeiro do agronegócio em sua área de atuação, respondendo por 54% do crédito rural na região. Atuando para promover o crescimento sustentável na região Nordeste, por meio de apoio financeiro às atividades agropecuárias, o Banco do Nordeste oferece linhas de financiamento com as melhores condições de mercado em diversas atividades, seja para custeio pecuário, custeio agrícola, máquinas e equipamentos, investimento, comercialização e exportação, agricultura irrigada, energias renováveis e armazenagem. O FNE, principal fonte de recursos do Banco do Nordeste, possui as menores taxas de juros do país, prazos diferenciados e bônus para pagamentos realizados em dia. Tudo isso aliado às melhores soluções, com opções de crédito diferenciadas para quem tem pressa de crescer. O cartão BNB Agro oferece crédito rotativo com agilidade e comodidade. Já com Planta Nordeste, você tem renovação automática do custeio, além de pré-custeio e comercialização. E para garantir um futuro sustentável, o FNE Sol financia sistemas de geração de energia renovável e redução nos custos de produção. O Banco do Nordeste possui soluções ideais para a atividade rural. Por meio do FNE Irrigação, apoia empreendimentos que desenvolvem a agricultura irrigada, fundamentais para o crescimento da região. E para quem quer manter seu empreendimento sempre atualizado, o banco oferece financiamentos de peças de reposição e manutenção de equipamentos e veículos. No Banco do Nordeste, o futuro é agora. São diversas soluções digitais para simplificar e modernizar sua vida, como cadastro, conta corrente, simuladores de financiamento e login digital. E os pedidos ao fornecedor no cartão BNB Agro são feitos via mobile. É o Banco do Nordeste levando o desenvolvimento digital ao agronegócio. Com o BNB Agro Inovação, o produtor rural aumenta a sua competitividade por meio da incorporação de tecnologias e inovações no seu processo de produção e de gestão, como equipamentos de agricultura de precisão, máquinas autônomas e outros. O Banco do Nordeste tem uma política específica para o agronegócio, destacando-se apoio ao desenvolvimento do cerrado nordestino, incentivo à utilização de tecnologias de convivência com a seca e desertificação, apoio à logística de armazenamento da região, incentivo para ampliação de áreas irrigadas, apoio à pesquisa e à difusão de tecnologias para o agronegócio e estímulo aos projetos de micro e mini geração distribuídas de energia por fontes renováveis. O Banco do Nordeste e a Confederação da Agricultura e Pecuária do Brasil têm parceria voltada para a realização de ações integradas, a fim de ampliar e facilitar o acesso dos produtores ao crédito rural. Como consequência, o acordo deverá proporcionar a melhoria de renda e das condições de vida das famílias rurais atendidas na área de abrangência do banco. O banco mantém ainda parceria com empresas fornecedoras de máquinas, equipamentos e insumos agropecuários para possibilitar a modernização do setor. O Banco do Nordeste atua em estreita parceria com o Ministério da Agricultura, Pecuária e Abastecimento, apoiando os diversos programas do governo federal por meio de sua ação financiadora em consonância com as políticas públicas. É tudo isso e muito mais que faz do Banco do Nordeste o maior parceiro para acelerar o desenvolvimento do agronegócio.
Good afternoon, everyone. Boa tarde a todos. Obrigado por participar do Inovagri e também dessa sessão, onde nós vamos falar do uso de informações hidrológicas por satélite e também medições tradicionais. Eu vou falar em inglês, a sessão vai ser em inglês, e eu vou, a partir de agora, falar inglês, e se vocês me permitem, o George Burba, que é um dos palestrantes, não fala português, então nós optamos por todo mundo falar inglês. Muito obrigado. Okay, good morning everyone. I just said a few words in Portuguese to the public to explain that we are going to be using English as the language because Dr. George Burba doesn't speak Portuguese, and so the presentations will be in English. And so the session today is about combining satellite and ground-based data for hydrologic monitoring. I will give a short presentation on that, and then Dr. Burba will talk about evapotranspiration and other measurements using flex towers. Dr. Ivo Zution Gonçalves will talk about using remote sensing for evapotranspiration and yield estimation. And then Jessica Garcia Nascimento will also do a case study of using remote sensing and ground data of hydrology in the state of Paraná. So all these presentations have a theme, a thread of using orbital or satellite data combined with ground data. And then the idea is to show the power of using these data sets together. So on to the first presentation. I'm going to be giving you an update on this topic. I'm the Director of Research of the Dougherty Water for Food Global Institute at the University of Nebraska, but I was born in Brazil and do speak Portuguese, as you probably heard at the beginning. What I will be discussing today is advances in using remote sensing in hydrology, and then give an example of a couple of projects that our institute's involved in that are pertinent to this topic. The Parallel 41 Flux Tower Network to measure actual evapotranspiration, and then the GLODET satellite-based ET product and how we are using it now in Brazil, and that will tie into Jessica's presentation as well. So let's move on to data in hydrology. If you look at this interesting graph by paper by Overpeck et al. 2011, where they point out the huge increase in availability of hydrologic data. If you look down here, the green bars, which is very narrow, is the in situ measurements, right? The in situ measurements of climate, of precipitation. But then with the advent of satellites, the blue bars is producing a huge amount of data that can be used in hydrology and climate, right? For precipitation, temperature of the surface and other. And then you have the models, the general circulation models, the regional climate models. So all this is producing huge amounts and petabytes of data, right, that are available now for hydrologics and climatic studies. Anyway, let's look at the main components of the hydrologic cycle, precipitation, right? As you know, typically in the past, we've had gauges, rain gauges that collect the precipitation locally as a point measurement, okay? This is an example of the network in Nebraska over here on the left. And then you have global networks of precipitation gauges, right? This is what it looks like in North America, meaning Canada, US, and Mexico. And then you have networks throughout the whole world, inclusive in Brazil, right, of precipitation gauges. Then came weather radars, right? Back a couple of decades ago, a few decades, weather radars came into effect, used in aviation, but then these instruments were calibrated with those rain gauges and now produce spatial precipitation that is quite accurate. And that gives us another level of data, spatial data to be used in hydrology. Then came satellites, right? First, the GOES and the Meteosat had a thermal IR sensor that was calibrated to produce precipitation of large storms, mostly convective storms. Then we had passive microwave sensors on satellites like the SSMI and the AMSU. Then came the TRIM program, also passive microwave, and then came a radar from space as well. And all these satellite missions measuring precipitation have produced quite a bunch of hydrologic precipitation products. Here's a whole bunch of lists, and you can go and look at these references, right, of these different products. Some are look back in time and do reanalysis. Some are real time, okay? But there's quite a large amount. And one product that is going to be discussed today by Jessica is the Emerge product, right? Which is a quite new, recent product that uses satellite passive microwave data from all these satellites and produces a 30-minute preset globally. And then she's going to show how she used that data. So the Emerge is a global data set and quite an interesting data set to be used. Another aspect of this hydrologic water balance is soil water content. Of course, as you know, we have point measurements of these in the fields that you can use using different technologies, neutron probe, TDR, tensiometers, heat dissipator, right? There's different ways of measuring point measurements in the field. But there's also satellite products, right? Like the SMAP, the soil moisture active passive global soil moisture product. Of course, this product is giving us soil moisture just on the very, very small, narrow surface layer of the soil. But of course, if you have a sequence of it, and you can model what's happening below, and if you have precip to go along with it, you can do a pretty good job of modeling what's in the profile. Groundwater, another important segment of the hydrologic cycle. Here's an example of Nebraska, where all these dots are observation wells. Some of them, like the blue ones, are measured hourly. Some of them, like the red ones, are measured daily. And then the black dots are measured twice a year manually, okay? All this information gets gathered and used to produce groundwater maps, okay, throughout the whole state of the High Plains Ogallala aquifer. This is important because center pivot irrigation pumping from this aquifer is about 85% of the irrigation in the state of Nebraska. That's over 100,000 wells, right? So there's a lot of pressure on the groundwater, as you could see here. Up to 1981, a lot of the areas of the state, the aquifer had dropped several meters, okay? But with the advent of the natural resource districts flow measurements, okay? For example, in an Upper Republican NRD, every single well has a meter. some of them use telemetry to submit data in real time so that control can be made on each well, and there's a cap. They're only allowed to pump 300 millimeters a year, so they have to produce corn and other crops by managing the precip that exists in the semi-arid part of the state, along with irrigation. But this is an example, and Ivo is going to give you an example of how this data was used. Okay, if we look now at groundwater in Nebraska, it's fairly stable. Okay, the water table has recovered in many places, and only in the Republican River in the northwest of the state we still have problems. Stream flow, another important variable of the hydrologic cycle. Okay, you have precip minus ET. Some of it infiltrates, some of it runs off, and it's important to measure. And this is an example of the network in Nebraska, automated. Some are USGS stations, some are Nebraska stream-based stations. And there's different technologies. Some of them have acoustic Doppler profiles, measuring gauges, some of the traditional stage gauge relationships and automated that way. Then moving on to another hydrologic important variable, evapotranspiration, and you know that there's automated weather stations. Here's an example of the CIMIS network in California. Hey, these are all weather stations that are gathering the data that you need to run the, for example, the Penman-Monteith, the reference ET equation, right? In the Central Plains in Nebraska, we have a similar network, okay, which is shown here. And we can go on and get the data in real time and use it for irrigation scheduling purposes. Then there's networks measuring actual ET, and this is the Parallel 41 Flex Network project that I was telling you about, I was going to mention. You see these colored pins going from Iowa all the way to Colorado. There's a gradient of precipitation here from the fully precip rain-fed crop production here to the arid west, where you need irrigation to produce corn, for example. And so you have this gradient of precipitation, and we have eddy covariance flux towers, right, measuring in real time the evapotranspiration of these fields. Some of these towers are in corn, some of them are in soybeans, some of them are in grasslands, okay? And everything, here's an example of a mobile tower out in Grant on a cornfield. And we have all the equipment to do the full energy balance. And I'm going to let George Burba in his presentation describe and explain what all this means and how it's used. But this is a product from LI-COR Flux Suite, which allows us to show the data being corrected by SmartFlux in real time at each tower, which is also a LI-COR product. All the corrections are being done in real time and then served out with Flux Suite. And you could look at the data in real time and put quality control flags. Dr. Burba is going to go into more details. You could look at it on your smartphone, but only the investigators really have access to SmartFlux. What we have done for the growers and for the farmers and for the water managers, capture that real-time data and put it in our Parallel 41 Flux Network website, okay, which you could go on there, you could register so that you can have access to the data, and you can choose any of the towers, the ones in Iowa, the ones in Meade, Nebraska. Here we selected the one in Grant, okay? And you could look now at the daily ET data. In this case, you could choose millimeters or inches, okay? You could choose millimeters or inches, and of course, farmers in Nebraska are interested in inches. That's the unit they're used to. And you can look at seasonal data of reference ET, of actual ET, of corn in this case for that particular field. So one of the goals of this network not only is to provide this real-time data in this gradient of precipitation across the Central Plains, but also to ground truth and anchor our daily ET precipitation, daily ET product, which we're producing on the supercomputer here at UNL. We're running the Alexi model, and this is in partnership with Martha Anderson at USDA, Chris Hain at NASA, Mitch Scholl at the University of Maryland, and of course, funding from the Water for Food, myself and others involved. And we originally got funding for USAID with partner Zic Bonini to do it in the North Africa and Southern Mediterranean countries in real time. So this is daily evapotranspiration using the VERS satellite, okay, which is a new satellite that is coming, substituting the MODIS. And it uses the thermal IR satellite band of the VERS satellite. As you need an energy, you need this in the Alexi energy balance model. And we can come up with products like this, right? The daily, the total ET or the total annual ET for the whole region, right? Estimated by integrating the daily values, right, over time, okay? So this is an example. You see here the Nile Delta, where the ET is quite high because there's surface irrigation in the Nile Delta, and it's in an arid region, right? So here is the final product that have developed is the DisAlexi, the disaggregation of Alexi, which we are producing at 375 meters globally and using Landsat imagery to disaggregate to 30 meters, right? So we can get daily 30-meter values of ET using Python DisAlexi. So it's going to be an open source software which Mitch Scholl developed. Now, the daily ET is produced on 15-degree by 15-degree grids, right? So we can turn on grids in different parts of the world as we get funding and availability of resources. So here's the grid in the Central Plains of the US along the parallel 41 flex network. Here's an example of June 16 in Nebraska. So this is the VERS Alexi product. And we did it here because we have eddy covariance stations, right, in Meade, Nebraska, that we want to compare the data to, right? So here you see the Alexi ET compared to the measured ET from the flex towers, right? And this is at 375 meters. So this is a preliminary comparison. We still have to do the disaggregation to do it at 30 meters where we can use the footprint that George Burba is going to explain in his presentation. And we're producing it now in Brazil, okay? So with funding from CAPES and ANA, as you know, the ANA is the Brazilian Water Agency, and partnerships with USP, who is leading this project, Universidade Federal do Rio Grande do Sul, Universidade de Santa Maria, and the Sulflux group, and INPE. We're producing now the GLODEC product in Brazil on these tiles, right? 29, 30, 53, 54, and 77, where we have several eddy covariance flux towers and partners, and doing some comparisons, right? So here's an example of the product over tile 153 and the state of Paraná. And Jessica Garcia is going to show you how she used this Alexi data in her research in the last presentation of the session today. And here's some comparisons using the Sulflux towers. This is Deborah Roberti and Anderson Ruhoff did this comparison of the Alexi VERS against the eddy covariance in different crops, right? Natural grassland, rain-fed, natural grassland in Pedras Alta, irrigated cropline, and the preliminary results are very, very encouraging. Of course, we expect this variability to decrease once we go to 30 meters using the DisAlexi. And here's a sugarcane tower by Humberto Rocha from USP in São Paulo. Again, we see similar results. The Alexi model doing a fairly good job around the one-to-one line. And here we've already done some preliminary downscaling with DisAlexi, and this is what the image looks like and this is the zoom in over that sugarcane field. Okay, of course, the image over here on the left was at a different date than the Google image on the right. So this is sugarcane, and as you know, the talhões get cut at different times and so forth. But this is the product eventually that we're now going to compare at 30 meters with a tower. So we have other partners that have towers in the Cerrado, in the Caatinga. Humberto has towers at the Atlantic Forest. And so we're going to be doing these comparisons. And additionally, we're going to run this product in tiles, in those other tiles, and put it so that other people can have access to do your research. So as final comments, I want to say that satellite remote sensing has vastly improved the ability to use spatial data in hydrologic studies, and that combined with the ground-based measurements of hydrological variables is a really powerful tool for water balance studies, for for evapotranspiration, irrigation scheduling, and so forth. Eddy covariance is a very useful technique to provide real-time data, and we're using that then to anchor our satellite-based ET with these eddy covariance towers and increase the accuracy of the spatial product. That's the goal, okay? So they provide a very important ground truth for verification. So that's all I had to say. Thank you very much. I am going to stop sharing my screen. I don't know if there are any questions right now in the chat box for me. I have forgotten to mention for those that are attending that you can ask the presenters questions in the chat box, right? Okay, so have I stopped sharing my screen? Yes? No? Hello? Okay.
Yes, Chris.
Okay, so if there's no questions, let's move on. You can have a chance to answer any questions. I'll have a chance at the end when we have the panel section. So let's move on to the next presentation by Dr. George Burba from LI-COR Biosciences here in Lincoln, Nebraska. And he's going to talk about flex towers and all the beautiful things they can do. George, you have the floor.
Okay, I hope you can hear me.
Yes, we can hear you. You can raise your volume a little if you like.
Okay, can you hear me better now? Hello?
Yes, okay.
Okay. So Christopher described all these scientific studies and satellite products and some of the direct measurements which have been done about evapotranspiration. And here I will describe the latest technology behind these direct measurements for evapotranspiration, for CO2 uptake, for methane release, for computing light and water use efficiencies, because the same effectively flux station does all of these things. And then we can discuss a little bit about the networks of stations and what tools are available there, and the analytical programs. When you have so much data, how you make something useful out of this huge amount of data. So at present, there are hundreds of flux stations. They operate standalone for very particular research. They also operate as a part of larger networks. At the same time, there is a wide scope of remote sensing data currently available. As Christopher have shown this plot from 2011 paper, there is tremendous amount of remote sensing information available in comparison to the direct measurements. So there is a big value of coupling the flux station data, the direct measurements data, and remote sensing data. And it's been outlined for years because the flux station only covers very, very small portion of the area. It's almost a point measurement, but it's very accurate. and remote sensing, it covers much more practical areas, large areas, regional, national, global, but it's less accurate. So by combining the two, you can have very accurate measurements and at the same time very broad coverage. And despite all of this, most of stations do not allow straightforward coupling with remote sensing data. For example, very few have optical sensors for validation of satellite products and additional measurements upscaling from field levels. And very few stations can even tell you where the flux exactly is coming from, because flux is not coming from the station itself. It's coming from the area upwind from the station. And that area is changing every 30 minutes. So I will describe a new system which collects data, processes data, helps analyze data, helps share data for flux and optical and weather and soil measurements from multiple stations at the same time. And the hope is that it can substantially help to couple the flux measurements with proximal and remote sensing data. So let me quickly describe you what flux station is. It's almost like weather station. So it measures temperature and relative humidity, it measures net radiation, but in addition to this, it measures also fluxes, the vertical transport of entities. So it measures evapotranspiration going in and out of ecosystem. It measures CO2 flux going in and out of ecosystem, and it could measure methane flux as well. So if you're not very familiar with flux station, basically treat it as weather station with additional flux measurements, some soil measurements as well, and the computed products. There are instantly computed products like radiation use efficiency and water use efficiency, for example. There is a computer on the station checking through the data. So in a little bit more detail, let's look at this grand scheme of data from the point when it's being collected to the point when it's being basically used for decision making. So the blue here is the available hardware and software. That's what's available now. The green is the new resulted functionality. The green means, okay, after you have the software, what you can do. And some people do it and some people don't do it, but you can do it right now. And the red is the opportunities for automated and semi-automated coupling of flux tower data and remote sensing data. So the red is not being very well utilized right now, partially because most of the people doesn't know it can be done. It's been so long, the struggle to couple remote sensing and flux data have been so long that a lot of people think it's not really possible without enormous amount of effort. But the parallel 41, for example, Christopher described, can do. That's what's in the red. So now let's go through each component of this. And then we'll understand how it all works. And then from that, you will understand how you can use it for your own needs. So first of all, there are multiple data loggers at the flux stations. And they can do soil and weather and light and optical and other sensors. So no matter what you want to measure, if you can plug it in the data logger, it can go eventually into the flux station. So it's all automatically flows through here. And here you can have a lot of remote sensing type of data. You can have on the tower, like pictured here. And then you can have more standard radiation outputs, and then you can have products and indices as a result. Some of it is easily available, like albedo and APAR. Some of it becoming available this year, like in DVI and PRI. The CIF is slowly getting into these measurements. There are more difficulty with it. It requires additional own processing. But the basic message here is
Hello.
Olá.
Looks like we have a little problem.
I think we have a problem with internet with
Yeah, George disappeared.
George. Yes.
Okay, well, let me call him and see what, and meanwhile,
Christopher, if you prefer, you can reply some questions.
Sure.
And then we will have we will ask.
Sure. So are there any questions for me? Let's see here. Okay, I don't see any questions at this point. I'll look in the question and answer chat also.
Did you guys, where did you guys lose me?
Oh, okay, George, you're back. Good. We lost you at the slide that you were spending quite a bit of time on.
Okay, so because I didn't, it went very silent, but I probably didn't catch it right away.
Yeah.
And now I cannot share my screen. Host disable participant screen sharing.
Wesley, por favor, vê as permissões para o George. Ele teve problema de conexão e retornou.
Ok, é porque, beleza, não estava voltando aqui para mim ainda, George.
George, are you okay now? Do you have control?
Yes.
Okay, go ahead, and if you bring up your presentation, we'll tell you where you were.
Okay, because I've been talking. Okay, here.
Yeah, you were on that. Yes.
Here. Or the next one.
Yeah, that one. No. You were back. I think this is where you should start off from.
The smart flux one?
Yeah.
Okay. So, at the core of the station, there is a computer called Smart Flux. It's basically a weather-resistant field microcomputer. It acts as a brain of the station. It accepts all the data from all the loggers, and it acts as a processor. It processes all the fluxes. It merges all the data together by time. It does real-time processing and all the corrections and everything else you need to get you the final data, final fluxes merged together with the weather data and soil data and radiation and remote sensing data, if you have any at the station. So at the end of each 30 minutes, you have everything in one single file, including exact GPS time, which is very important for remote sensing validation, including coordinates of the station, which is very important for remote sensing, including the actual area where the flux came from. And you can see it, I will talk about it more. Station is here, but flux is not coming from here. Flux is coming from here, upwind, the area upwind. And every 30 minutes, the smart flux computes where exactly it came from. So when you match your pixel from the satellite, you don't match it to this, you match it to this area, to this blue and red area here. So the paradigm is exactly like the weather station. Everything is in real time and everything is final, except in addition to weather, you have your fluxes and soil and radiation and whatever else you plug in your loggers for remote sensing or modeling. So all of this together is automated flux station. Now, when we have one station like this, it's fairly easy to operate. But when you have multiple stations like this, it's much better to operate with a special software tools. And the tool is called Flux Suite. So the flux suite, Christopher also shown examples of it. It lets you connect many of the flux station into single network on exactly same time. Everything is GPS satellite time with exactly same processing, and you can see all the data in real time. And in addition to controlling your stations, in addition to receiving alerts and everything else, you can share your data in real time or not share your data in real time with various particular peoples or groups. So it gives you a lot of flexibility what happens with this real-time flux data after the data been collected and computed. Here's an example from this grant Nebraska. That's how the front page of Flux Suite looks for one station. You have your station name, you have your standard index for the station, location, coordinates. You can put in what kind of crop is this and so on. Whoops. And it lists you all the instruments, and there are field logs, what's been done, what needs to be done, and so on. And Christopher have shown this one already. You can see your past couple days of data, or you can see as much data as you want with quality control and without quality control. Then, of course, if you have multiple stations and you manage them like this, you have multiple stations running Smart Flux, you manage them with Flux Suite, and they run most of the time, you have a lot of data to analyze. And analysis is different simply from collecting and processing and getting fluxes. Now, what do you do with these fluxes? And here we have the software as a part of this total solution, which let you analyze the fluxes in a very sophisticated way. And I give you one example of how sophisticated it is. And that software called TOVI. Bear with me here. So this example is a little bit long, but if you understand it, you will see how sophisticated the software gets and how you can apply it to remote sensing. So this is the station, the little star here in the middle. Can you see my arrow, by the way? This arrow. I hope you can.
You're using a pointer, George?
Yes.
No, I think you might use the mouse. Try using the mouse.
Okay. Okay, let me try.
Yeah, we could see the mouse. You're out of presentation mode now, I think, though.
But when I'm going to presentation mode, you cannot see.
Yeah, we could see the mouse.
Okay, the mouse. Okay, so this is the station here. This is the station. And this is the footprint. In summer, it's mostly from the south. And in winter, it's mostly from the north because of wind direction. That's where the fluxes are actually coming from. And this is the peak of flux. So if you do any type of satellite merging, you will do it in summer, probably to this point. That's the most correct flux from this grass. This is the grass. So in the software, typically, without this software, typically what you will see if you go to flux database like FluxNet, you will see fluxes from this grass page as this gray dotted thick line. So you can see that there is a CO2 emission here. Anything above zero is emission. Then during daytime, you see a little bit of photosynthesis, uptake of CO2 by the grass, and then it goes into emission again. So if you don't have this type of sophisticated software and station doesn't have the measurements to allow to use this software, that's what you're going to see. That's what your satellite merging and modeling will be based on. That's what's being done now. But with this software, you can select this perimeter. I selected this perimeter, green, and say, okay, only show me data when fluxes come from the green perimeter. I've also selected the red, parking lots and roads. And I said, now in separate set of data, only show me fluxes which come from this red perimeter. So this would be like a pixel for your satellite. You can choose any type of shape you want, and you can choose multiple shapes. And the same exact data is in this green, in this gray line, now are broken in two separate sets of data. the green grass and the roads and parking. And look how different they are. So the green grass behaves in predictable manner. You have respiration at night, much bigger, like 3-4 times bigger photosynthesis, actual photosynthesis during the day, and respiration at night. So if you simply go to Flux database and try to model, you will be multiple times off compared to what actually was happening there. At the same time, for the traffic, you see the morning peak when people go to work. You see the evening traffic peak when people go from work. There is no photosynthesis anymore. Everything in the red line is above zero. It's all emission of CO2. And on certain days, you can even see the lunch hour. It's not very pronounced here, but if you look at the individual days, you can see it. And when you compare this emission and traffic count, you can see how well they overlap. The blue is traffic count. So suddenly, literally with few clicks and few perimeter selections, you can do very sophisticated analysis using this software. And that's only one tool in that software. You can do multiple other things not related to the footprint. And for sake of time, I'll continue here. So now you have your measurements from the Flux stations with exactly the exact location you know. So you can start matching them to the remote sensing data. So you have your remote sensing data where each pixel has spectral data, multiple data products, recomputed model outputs like Christopher described. From the station data, Flux station data, you see the footprint, the area where it comes from for every 30 minutes. You can see all of your fluxes, radiation data, weather data, soil data, and whatever else you plugged into the data logger. There are a lot of proximal data. So now you can precisely match two sets of the data. The ground data, directly measured, but point sources of data, and the remote sensing data. It allows you to do a lot of things. Here are just examples. Of course, there is much more things you can do. So you can have a variety of products depending on your research goal or your monitoring goal, from CO2 fluxes and ET to pigment indices to chlorophyll content in the canopy and so on and so forth. So in summary, how does it work again, this new system to do that? Each single Flux station measures all parameters needed for a particular research goal. The field microcomputer calculates fluxes every 30 minutes, actually. And it computes other important products and quality controls and footprint, where everything's coming from. The Flux suite links multiple stations into one single network, so you can manage it with few people, and also you can use it a lot better with remote sensing. Just a second. The Flux Network Manager, the PI, sees all the towers, all the fluxes, and all the weather data, and receives the alerts and emails if something's wrong with the data. And also the PI can restrict or allow certain information from the station to go in real time to somebody else. Similar like weather station data, they go to for example, to Boulder, Colorado, to supercomputer to get processed and get prediction models. So what can already be done on the ecosystem scale with these tools? This doesn't require much effort. This already can be done. Because you have GPS-driven precision time protocol in each station, you can precisely align remote sensing and Flux data in time. Because footprint size and coordinates computed, you can precisely align remote sensing and Flux data in space. And because you can connect so many remote sensing related measurements into the data loggers, you can create full snapshot of remote sensing pixel and describe it the way you want for your research. And it includes leaf level, ground-based optical sensors, and fluxes from same exact footprint. Everything is in that pixel in exactly that time when satellite data are available. And inside footprint, you can also start scheduling measurements, which was very difficult in the past. You can, if you need to do leaf level measurements, leaf chamber or soil chamber, you can go to your station. You can go inside the footprint depending on the wind direction, exactly at the time when satellite is flying over. So you can do the leaf level measurements or soil chamber measurements in the footprint at the time of the overpass. And what can be done already with multiple sites on much larger scale? First of all, many hundreds of smart flux stations already operational, and most of them already online. You just need to ask PIs to have access, so you can use them in the modeling and remote sensing validation and so on. Then in addition to these multiple hundreds of smart flux stations, there is more than 600 active flux stations in the world, typically using older technology, but data is still available. And this is in the FluxNet database. And these are active now, 600. And in addition to this, there is more than 2,000 all the flux measurement locations, which can be used for analysis and tuning the model and evaluating the remote sensing products. And they spread around different databases, but if you need some help, I can help you. Just email me about this. This is the golden egg, and nobody's using it. There is so much interesting data in there. The entire world is covered. And what's being done already? And Christopher already described it in detail. What's being done already is this parallel 41 network, which utilizes all of these tools. When you have your stations spread around the ecosystem in critical places, this is just conceptual figure, but you have your satellite imagery, and you have your remodeled and reworked satellite imagery, and you can validate measurements from satellite as well as products derived from satellite using the direct measurements at the field scale. So the public product could be something like the weather apps, but in this case for the irrigation planning, where then people right now, they're using weather data, they can go and start using flux data, like how many inches of water has been lost in the last week. So farmer will put half of it or all of it in the field and not more than that, and so on. Also, this concept provides future possibilities, which are completely not addressed, but I keep presenting this until people start using them, because this is really valuable, and there will be a lot of leverage from this. So when projects are getting funded, they're usually funded for specific goal. For example, CO2 monitoring, and they form the flux network. But when you have a smart flux on the station, you can share one or more of the stations, as many as you choose. So another project may be funded for water, for hydrological application, or for agricultural application, evapotranspiration network. You can use the same station in two different projects by two completely different groups. And then it could be another project funded for methane emission measurements. So you might be able to use same station for multiple different projects with multiple different PIs, and each of them will get only the data they need. Like, for example, this station is located in a field, in a wetland maybe, where you have both CO2 and ET, and as well as methane, and they all fairly large in size and interesting to look at. So it can be involved in two. But other station might be only used for CO2 and for water and for methane research, but not for CO2. So this is peer-to-peer cross-sharing. This is not what's being used in environmental research. It's being used in computer research from time to time. But we can use it in environmental research and triple, quadruple, quintuple the value of single station, just because of how smart flux is computing things and how all of the smart fluxes are organized in the network. So for remote sensing and modeling community, it also provides opportunity to access data from flux station across the globe without having your own station. You literally can ask somebody, and I put here researcher in Brazil, the model in Brazil, if they study wetlands, if they study mangroves, they can ask PI in Southeast Asia, in Vietnam, and in Indonesia somewhere, and in Mexico, in mangroves in Mexico, in Florida and in Mexico. And this person can form the virtual network of actual mangroves flux stations like this. And this is not being utilized yet, but it should be utilized because it start getting science on the global scale in real time. And of course, another future possibility from this would be reframing the entire climate discussion. If you can have the irrigation planner, if you know your real-time water losses and water budgets, you can do the same for carbon. And you can do the same for ecosystem services. And suddenly you can have an app for the farmer who can irrigate better. But you can also have another app for no additional cost. You're using the same data. For sequestered carbon in your area, you can come in and see how much of carbon was sequestered by your forest, or how much water was cleaned by your local wetland. And suddenly if people start using these apps just out of curiosity, and time comes to make a decision to cut the forest or to keep the forest, to drain the wetland or to keep the wetland, suddenly the public opinion may be very, very different. They will keep the forest, they will keep the wetland. And that will come through grassroots movement because people will simply understand much better what the ecosystem gives them. So that's all I had for this. Thank you very much.
Thank you, George, for that presentation. There's a question in the box that maybe you can address it right now.
Sure.
He's asking if TOVI, this is from Otavio Neto, he's asking if TOVI is an open access software and how we can get it. Well, I know the answer, but you should probably answer that.
Yes. So because people stealing from us, TOVI is everything in TOVI. The engine is open access. The engine you can use. The graphic user interface is closed access. But let's write back and forth. TOVI is subscription software, but you can have fairly long trial when you can use it, and basically the trial will gives you the opportunity to do analysis.
Okay. There's one more question before we move on to the next speaker by Elzimio Fraga. He's asking, how could we transfer this technology to farmers here in Brazil?
Oh, that's probably a question more for Christopher. My vision would be if you can start grounding the remote sensing and modeling products by towers in real time. You don't have to have towers everywhere. Your remote sensing and modeling products going to become better and better and better and faster. So you can start literally predicting water use and soil carbon content and things like this for large region. And on top of it, Brazil has enough towers. If Brazil comes in, then this tuning will be happening in real time on the national scale. Yeah.
Yeah, and maybe we can write a proposal to Anna to network a lot of these towers together, right? And do what we're doing with the Parallel 41 here in the Central Plains. Yeah. Very good, George. Thank you for that. And I'm sorry you had a little hiccup with the internet, but you're back and strong. So we will move on to the next presentation by Ivo Zution Gonçalves. Ivo spent 5 years here as a visiting scholar and postdoc with me at with the Water for Food Institute. He has recently returned to Brazil, and he is now at the Exalc, the USP in Piracicaba. He just started there on a funded project with FAPESP. And today he's going to talk about some of the research he did while he was here in Nebraska. Ivo, you have the floor.
Okay, thanks, Christopher. Hopefully you are hearing me and seeing my presentation, right?
Yes, we are. If you could raise your volume just a bit, that would be helpful.
Okay, so thanks, Christopher, for inviting me for this roundtable and Inovagri for the opportunity. I'm really glad for that. So my name is Ivo. I was working for Water for Food with Christopher since last 3 months, right? And I just moved to Brazil. I spent 5 years in Water for Food. Now I'm working for University of São Paulo as a researcher. So I'm gonna talk, going straight to the point, how to estimate evapotranspiration and yield through orbital remote sensing for irrigated agriculture, using also ground data, of course. So first of all, I split my presentation in a very short review. What is remote sensing? Also, I'm going to talk about the methods for estimating evapotranspiration and yield. And finally, I'll be showing some results from research we have done and ongoing research in Nebraska and some research in Brazil as well. So then a brief introduction about remote sensing. Remote sensing, we have the sun. It is the main source of energy we have. The sun emits radiation that reach the surface, and then this energy, this radiation, return into the atmosphere and reach the sensor, the satellite in this case here. The satellite sends this information to a central station for pre-processing the data. And then this information is ready for the user, in this case, us. Okay, and then basically, in other words, remote sensing is when you analyze a physical object without contact with it, okay? So we have many sensors, satellites all around the world available for the user. We have, for example, here, let me get the laser. We have here the very well-known Landsat 8, for example, Landsat 7. We have, for example, the CIBERS, the partnership between Brazil and China. We have some radar, GPM radar for precipitation, the very famous Terra modes. So those sensors, those satellites are distributed in different platforms, in different levels of platforms. Orbital data, when we talk about orbital data, we are talking about satellites and radar. Orbital data means spaceborne, okay, instruments in this platform. But also we have airborne platform when we have, for example, aerial photography. This one up to 10 kilometers above the sea level. This platform orbital, it is over 700 kilometers over the sea level. Ground-based, we have also ground-based. Here we have example UAV, unmanned vehicles. The best example, I think, is the drone we can have. And then the question is, which one is the best one for the user? There is no best or the worst. We can use all the platforms individually or together. It depends on your project. It depends on your research, your goal, what you are looking for, right? So those sensors, going with more details about the sensor, to be clear, for example, here we have this table. In this column, we have the satellite, the sensor, Landsat 8 in this case. The time resolution, different time resolution depend on the sensor. For Landsat 8, for example, every 16 days, they revisit. The image size almost 200 kilometers by 200 kilometers. And a special resolution for this sensor, Landsat 8, for the multispectral bands is 30 meters and thermal bands 100 meters. And then we have many varieties of satellites, many to be used in different projects, okay? So this is a very nice example I like to show. So for example, here we have a center pivot, large area. When we use the sensor only from Landsat H, we see we can have hundreds of pixels with many, many details. But when we have a coarse resolution, in this case, modes, a lower resolution, we see we have just few pixels. And then which one you have to use, it's depend on your area size, for example, your goal. But here in this case, it's still good modes. It still can be used. Now we know what is remote sensing. We know a little bit about the sensor, what's a sensor, and then we can talk about the methods for estimate evapotranspiration through remote sensing. Basically, we have three methods. The first one, it is about the crop coefficient and VI. VI is vegetation index. When we talk about crop coefficient and VIs, it is because there is a relationship between the vegetation index, in this case, SAVI, the very well-known SAVI, very common in irrigated areas. So at the beginning, the crop, the season, we have bare soil. This is in Nebraska. This is the day of the year. This is in February. There is nothing growing here right now. And then the vegetation index is very low. And then here in the middle of the season in July, the vegetation index reached the peak. And then we have the maximum VI. And then finally, at the harvesting time, we have again the NGVI very close to zero because again, we have bare soil. The NGVI follows very well the leaf area index. And then you see here nothing growing except cover crops or winter crops like wheat in Nebraska. Here we have basically corn and soybeans. And finally, again, we start the off season here after harvesting. The leaf area index is close to zero or zero. So, and then here, of course, the crop coefficient, the basal crop coefficient, transpiration is minimum. Here is maximum. And here again, drops a lot. It's minimal. And then we can see at the beginning, we have increasing the crop coefficient until the peak, and then decreasing drop until the harvesting. This is for corn, okay? This is for corn. Each crop has your specific curve, right? And then that's why this relationship are typically crop specific because each crop has your own characteristics, okay? This approach uses shortwave bands. In other words, visible and near infrareds, multispectral bands. There is no thermal bands in this methodology here in this approach. But, sorry for that. The energy balancing model, this is another approach, is based on this very famous equation, net radiation less soil heat flux is equal latent heat flux plus sensible heat flux. Based on this equation, we have one-layer models. A very good example, we have the SIBO, we have the metric, and the CBOP. The CBOP, ANA, right? The water agents in Brazil use CBOP for estimating ET, if I'm not wrong. We have two source model that we heard from Christopher, and we're gonna see in the following presentation with Jessica, the Alexi and Pides Alexi. This model, this approach requires the use of both thermal, infrared, and the visible near infrared bands. And then here we have the multispectral bands, and we add here the thermal bands, okay, for estimating the surface temperature. And finally, the last but not the least, we have the hybrid methodologies. What is the hybrid methodology? The hybrid methodology combine the energy and the water balancing models together, okay, to estimate the evapotranspiration. A very good example, I'll be talking about this model later in this presentation. We have SETMI. Okay, so this is some examples, some methods. I'll be showing you results, okay, using this approach. But now we know how to estimate evapotranspiration. We have to see how to estimate yield. So basically, this is the equation to estimate yield. First of all, we have to estimate biomass. Biomass, okay? Biomass, what is biomass? Biomass, it is the sum of the transpiration coefficient over season. In other words, accumulated basal crop coefficient over season, but considering the water stress and the temperature stress. This product from remote sensing, right, times water, normalized water productivity. So, and then we can have biomass. But what is water productivity, normalized water productivity? I will show you how to estimate water productivity from ground data. So here, first of all, we have to know, just for curious, the C4 crops like as corn, we have higher water productivity than C3 crops because the photosynthesis is more efficient for C4 crops. And then here, it is around between 15 and 20 grams per meter square. A good example is soybeans, I'll be showing later. So this one, it is from based on soil-water balance. This is the soil-water depletion, water stress. After ready available water, this coefficient drops. And then here, from here, it starts the stress. And then value lower than 1, we have stress. The same for temperature stress, which is based on the air temperature. Value is lower than 1, we have temperature stress. This is very common in Nebraska, right? At the beginning of the season, because we are still finishing the cold weather, right? And then now I can talk, we know about how to estimate evapotranspiration in yield. We can talk about some research results from ongoing, and we have done research in Nebraska and Brazil. First of all, Nebraska, why this research? Let's talk about that. It is because in Nebraska right now, we have the new hybrid varieties. And then we have to update the new relationship between vegetation index and transpiration coefficient. We have to do that for the new varieties, right? And then after that, estimate the values for evapotranspiration estimating and yield. So, and then what we have done. So this is the SAVI for many years, as you can see here. Many years, SAVI is a vegetation index. What we have here is bare soil for corn, and then the SAV increase until the peak and drop until bare soil value is around 0.1. And then we have off season that comes from October until April. It's a long period without crop growing in Nebraska. And then again, it starts growing and decreasing and so on until 2012. We have for irrigated corn, we have for rotation, irrigated rotation corn and soybeans, and then for rain-fed conditions, corn, no irrigation, right? Corn and soybeans. And then why we need the SAVI? We need the SAVI just because here we have the SAVI, and then from the ground data using the flux tower and the covariance tower, we can have the crop coefficient, the KCB, transpiration coefficient. And then for corn, maize, and soybeans, we can have this relationship. That's awesome. Why? Because now we have the new relationship, SAVI, KCB. We can estimate the KCB just using SAVI values over season. We have that for maize and soybeans. And then together, coupling with FAO 56 soil water balance, we can estimate the evapotranspiration and compare to ET measured in the field using the tower, the flux tower, we see the results is pretty good. Okay, and then for biomass in the same research, we see this is the equation for biomass we saw before, right? And then the yield, when I get the yield, when I multiply the biomass times a harvest index. When we don't have this harvest index, we used to use 0.5, but we can estimate from the ground data. So look that. We have the accumulated KCB over season, right? With considering all the stress. And here we have biomass from the field. And then we can have a relationship, accumulated KCB over season versus biomass. We have an equation. Do you know what is that? This is the water productivity for rain-fed corn, and then this is for irrigated corn in Nebraska. You see, this one is very close to the actual value we have. We have the same for rain-fed soybeans and irrigated soybeans. And then now we have the new values for the new hybrid varieties for corn and soybeans in Nebraska and USA. And then finally, we can measure the yield. And then here we have the measured yield in the field. This is in mid in Nebraska. This is the modeled yield from remote sensing. We see the results is very, very good. So now, if we have the new relationship, SAVI, KCB for corn, we can extrapolate, right, this data to the rest of the state for thousands of fields using satellite images. And then that's what we came up. What we have here, this is thousands of fields, as you see here. Sorry, this is thousands of fields. Every single circle, it is a field, okay? Red circle means dry years, in this case 2012, and cold colors, in this case blue, we have wet years, raining a lot in this case. And then what we have from remote sensing, from the new relationship we got, we have applied depth. What is that? The amount of water was applied in the field. This is ground data that came from the data that Christopher showed us. Remember the groundwater? They measured the groundwater applied irrigation in Nebraska. That's very nice because we can compare with the modeled, the required depth from remote sensing. And then what do we see here? The huge variability. Have a very huge variability. And then when, it's not good actually, but when we join all the fields into the year together, we have all the fields here. Now we have an average of the fields in a year, okay, into the year. And then what we see over irrigation in wet years, and we see under irrigation in dry years. We have basically two reasons for that. It is because there is a system limitation for center pivots in Nebraska. Why? Because the system is not able to apply so much water in very, very dry year. And then they apply less water than necessary, right? The crop water demand. And then probably they have a water stress, but they cannot apply because the system limitation. And another point, another reason is the water allocation. They have policies for the use of water. They have to pay to use the water if they extrapolate the amount of water they can apply, and then they apply less water than necessary in dry years. In regular years, they apply very good results here. We did the same in central Nebraska, still in Nebraska, but we were here in Upper Republican region, and now we are in central Nebraska. We did the same, but but evaluating two different irrigation systems, center pivot irrigation system or sprinkler versus furrow irrigation system or surface system. Okay, we did that from 2004 to 2012. Over 2,000 fields, irrigated fields per year, with a total 20,000 fields total. You see how remote sensing can do that, the potential of remote sensing. We can study large areas. And when we have ground data, as Christopher showed us, we can compare the results. And then basically, we have similar results, a very high variability, scattered data we can see here in all the three sites in Central Platte, Tri-Basin, Lower Niobrara, high variability. And then how to explain these results? We have the soil type. The soil type, for example, in Tri-Basin, there is no high variability in the available water holding capacity. And then we think it's not because the soil type changed a lot. Maybe it's because the farmers don't follow the weather conditions, the weather data, or something like that. So, but here we have a very high water holding capacity, high variability, you see? And then that's why we have more variability here than here, and here also very high variability, because the variability of the soil, the available water holding capacity is higher than Tri-Basin. Some growers, they applied 3 times more water, okay? And then this is a research, one of the research we have done, related to different irrigation systems. For example, we see the triangle means the triangle is furrow irrigation, and the circle is sprinkler, center pivot irrigation system. And then the surface irrigation system applied much more water than the center pivot system. Of course, we expect for that, because the efficiency of the surface irrigation is lower than the sprinkler. The same here and here in all the sites, except here, because here we just evaluate center pivot, okay? But the center pivot, you see, on average, was not too bad, you see? And then we see again in dry year under irrigation again in dry year for center pivots, for the same reason, I think, is because the system limitation.
Hi, Ivo. We need to wrap things up soon, okay?
Okay. So now talking about, I need to talk about very fast about the hybrid model. Hybrid model, SETMI, Spatial Evapotranspiration Modeling Interface, operates in ArcGIS, and this model run energy balancing model and soil water balancing model individually or together. That's why we call the hybrid ET model. Here, the hybrid model, the SETMI, we have the energy balance, which provides the ET coupling with the soil water balance here, model in SETMI, improving the soil water at the root zone, improving the results. This is some results here. Here, the red dots, we have the KCB from satellite images. We can interpolate the gap between the images, the gap filling, using growing degree days, for example, and have KCB daily, okay? And then we can see the overseason. And then we can have all the outputs for soil water balance. Also, we can have spatially values, especially outputs, in this case, images, where for all the images, as much image as we want. in this case, KCB, SAB full cover, evapotranspiration adjusted yield, water productivity, and water productivity based only irrigation. So this is my last slide. This is in Brazil for sugarcane. It is an ongoing research, okay, from Dr. Regiani and Dr. Professor Fernando Tangerino. We see the ET from the tower, the edge, and the model setting is very good from the energy balancing model. And then this is the hybrid model. Again, the soil water balance. We can have all the outputs. It's a very nice model. Oops, forward. Okay, and then that's it. Thank you so much, Christopher and Inovagri, for the opportunity. This is my contact if you want to send me a message.
Thank you, Ivo, for that presentation. There is a question for you, okay? A question from Renata Teixeira Mignoni from Unesp Botucatu. She is asking how many years of crop yield data should we consider to produce a robust and reliable model for estimating crop yield based on remote sensing data?
As much as you can, of course. If you have, for example, 5 years, it's depends the quality of your data also. But if you have 10 years, it's better than 5. But in this case, we use it like 9 or 10 years. It was enough.
And what is important to be considered when you're doing this research with the relationships?
Well, you have to collect the yield and biomass in all the stages of the crop. You have to take care about that to have a very good relationship. And you have to have a ground data, of course, because you have to compare also with the flux tower ET to have a relationship KCB and a vegetation index, for example.
So in other words, good ET data, good ancillary soil moisture, crop biophysical parameters data. And,
at the beginning, actually, it is too much work, but after that, you have a new relationship. You can use this relationship for many, many, many years for many, many environments.
Very good. Okay, so we're going to move on. Thank you, Ivo, for the presentation. We're going to move on to the last presentation of the session by Jessica Garcia Nascimento. Jessica, you have the floor.
Okay, thank you, Christopher. Okay, hello everyone. I am Jessica. I am a current PhD, I'm agricultural and environmental engineer, and I am current PhD candidate at Exalc USP, and I'm also visiting scholar at the Water for Food Institute at the University of Nebraska in Lincoln. I will talk with you today a little bit of the working that we have been doing, use the remote sense in hydrology, and I will share with you a case study in Paraná, Brazil. But first, I will give you a short introduction about the water resource management. The main objective of the water resource management is to guarantee the water availability for all the activities that needs water. For example, for irrigation systems, for urban and animal and industry supplies. And we have to make sure that when it's necessary, we can have all these activities working at the same time, avoiding conflict between the use and between the users. So as commonly instruments used in the water resource management in Brazil, we have the charge for the water use, and we have the water rights, that in Portuguese is outorga. And for the water rights, we have to know about the water demands and the water availability. Or in other words, how much water do we have and how much water do we need? So in the traditional methods, we can obtain the water availability from the permanence curves that give us the volume of the water over the time. And for that, we use historical series for the historical series data that we obtain by the gauges or stations, as Dr. Christopher Neale said in his presentation. But here we have a limitation in our system regarding the density and the frequency of observation, especially in developed countries in South America. And when you don't know about the information about the water availability, you can result in a not so efficient management, and you can have the water scarcity. Since the water scarcity don't means just when you don't have water. It can also represent when you would need more water than you actually have. So here you can see better what I was saying about our limitation in about the density and extension of our rainfall and stream flow data. Here in the colored maps, you can see that most part of Brazil, we have less than 35 years of data of observations. And this, in the gray map, you can see about the density of data. You can see that some regions in Brazil, we have one station represent 8,000 square kilometers. So you have to analyze if this information, is it enough to be used in our management? Is it enough to be used in our hydrological studies? And we will see that in the most part, it's not enough. And because of that, the professionals of the area and the hydrologists usually use hydrological models to predict the variables, the hydrological variables that is important to us. For example, we can use multiple linear regressions and machine learning techniques to estimate dependent variables, for example, the annual discharge on the rivers, using independent variables to build relationships. For example, the slope and the area of the watersheds, the precipitation, and the evapotranspiration data. And we can also use the simple water balance to estimate the same variable, the same hydrological parameters. And that in this water balance, we consider the watershed as a closed system, and we have to know about the inflow and outflow of the water in the system. For example, the inflow here is the precipitation, and the outflow is the evapotranspiration, the annual discharge, and the variation of the soil storage, the water storage, water storage through the soil. So here we have our problem solved. And the remote sensing is an important tool that gives us all these informations that we need. For example, the slope and the area of the watersheds we can obtain using the digital elevation model. And the variation of the storage of the water through the soil, you can obtain use the images from GRACE that give us all the mass of the water over the world. And especially for the precipitation and evapotranspiration, we could use the precipitation data from iMERGE, as Dr. Christopher said in his presentation. It's the last version of this iMERGE is new. It was available to the public in October 2019. Its data is from 2000 to today. Its resolution, spatial resolution is to 10 kilometers, and you can obtain data from 30 minutes daily and monthly scale. And because of the high resolution, you can use in hydrological studies with great accuracy. On the other hand, the evapotranspiration data, we can use the ALEXI data. Here I will just give you a short review that is based on the two-source energy balance and allows the evapotranspiration estimative using the remote sensing product. And two inputs variables derived from the remote sensing are the keys of this model. There is the surface temperature and the fraction of vegetation cover. and its spatial resolution is 375 meters, and its data is available in daily resolution in our loaded platform in this website. So now I will show you a case study in Paraná using the Alexi data and the iMerge data. For this study, we use the iMerge data version 6 in a daily and monthly final run products. This final run products is very interesting because it's available to the public after a recalibration using the gates over the world. And we will use 511 gates from the ANA, and we are analyzing data from 2000 to 2018. So first, analyzing the temporal and spatial distribution of the precipitation estimated by iMerge and observed by gauges, we can see that the iMerge can predict very well the precipitation over the Paraná state. It was very consistent with the data observed by the gauges. For example, in January, February, in our wet season, both detected greater volume of precipitation here in the coastal area in Paraná, and in October here in the southwest area, and both detected in a dry season from June to August, a dry area here in the north of the state. So analyzing the daily and the monthly products, we can see that the monthly products overperformed the daily products, and it's understandable because in daily scale we have more variability of the precipitation in a short distance. And looking here, our monthly relationship between the iMerge products with the gauges, we can see that we had a good R squared equal to 0.73 and a good correlation equal to 0.885. And we also used qualitative indices to know more about the performance of this model. We used the probability of detection of rain and the critical success index. For these two, the best value is 1, and the false alarm ratio and the best value for this index is 0. And we can see here that the monthly products performed almost perfect to describe the monthly precipitation. So here we can see the spatial distribution of our statistical metrics, and we can see that in the continental area of the state, the iMerge daily and monthly products performed very well to predict the rainfall. But here in a coastal area, we have more errors and less correlation coefficient. And it could be explained because here we have mountain areas, and the satellites usually have a limitation to discriminate the adjacent pixels of land and water, and could result in signal contamination in these areas. But here, looking at our qualitative metrics, we can see that it was almost perfect for all the state in a monthly product. So because of that, the good performance of the monthly products, we will use the iMerge precipitation data in the monthly resolution, and we can obtain here in the website, the NASA website. And for the evapotranspiration, we will use the Alexi data in a 375 meters and daily resolution that you can obtain here in our address. And for that, we want to estimate the annual discharge over the watersheds in Paraná, Brazil. And for that, we will use just the water balance equation, where the precipitation is equal to evapotranspiration plus the discharge on the rivers and plus the variation of the storage of the water in the soil. Here, we will consider this variation equal to 0 because we will consider an annual scale, and the variation tend to be equalized over the year. So we have the discharge is equal to the precipitation from iMerge and minus the evapotranspiration from Alexi. And the main advantage of the use of this this model is the use of the free data from remote sensing hydrological model as a tool for water resource management, and also the simplicity of this equation. And we will compare our estimated annual discharge to 28 fluviometric gauges from ENA, and we will use time series from January 2013 to December 2014. And here on our first result, we can see looking the R squared and our Pearson correlation, we have a very good performance of the model to estimate the annual discharge, with a little bit of tendency to overestimating 12.9% a year. So trying to analyze if this model could be applied in a small and the big watershed, we divided the 28 watersheds in small, when the area was smaller than 5,000 square kilometers, and big when the area was bigger than 5,000 square kilometers. And we want to understand about the slope, if the slope could affect the model performance. And for that, we divided the 28 watersheds in flat to soft wave slope when the slope was lower than 8%, and wave to strong wave when the slope was higher than 8%. So we can see here in this picture that our model performed in a similar way in both groups of area and both groups of slope. And lastly, we evaluated if the land cover could affect the model performance. So we divided our 28 watersheds, our sample, in 3 groups of land cover: forest, soybean, and pasture. And we used the 25% as a limit for forest and 15% as a limit for the soybean and pasture. And we select this number based on the median of the watersheds. In other words, we wanted to keep in each group here the same numbers of watersheds. So we observed that when you have more forest or more pasture or less soybean, the model performed better than in the opposite scenario. And it could be explained because of many reasons, but the main is the forest and the pasture, they have a filter effect that helps the infiltration of the water through the soil, and it reduces the runoff on the surface and keep more constantly the discharge over the rivers and over the year. On the other hand, when you have more soybean, you have more dynamic of the use of the land cover over the year. So because the soybean is an annual culture, so it's just in the land for a few months in a year. So you have more variability of the infiltration and the runoff on the surface, and also in the river discharge. So it's our first results, and now now our next steps, we are go deep, trying to understand better the relationship between the land cover and the water balance. So thank you so much to Inovagri for the opportunity. Thank you to Dr. Christopher Neale to invite me to be here today, and thanks Ivo to be with me in this research.
Thank you very much, Jessica, for this nice presentation, rounding off the session where we discussed the uses of ground measurements of hydrologic variables together with remote sensing. I am looking for the questions on the chat to see if there's any questions specifically to you. Hold on. You mentioned that in some next steps you're going to look at additional influence of surface cover and vegetation cover. what are you thinking of doing next in trying to explain your results?
Yeah, we are because here we consider the forest as a forest plant. I say in Portuguese because I don't know, the floresta plantada e floresta nativa. So we are trying to make sure about the difference of the infiltration, about all the system between these two crops, the two florestas.
Okay,
forest.
so in other words, you, in your analysis, you bunched together natural forests like the Atlantic forest with eucalyptus forest that's planted. And now what you're going to do is separate those and see how that changes, right?
Yes.
I understand. Very good. So we are down to the last 20 minutes of the session, which gives us at least 15 minutes for additional questions from the attendees. So I encourage you to type your questions into the chat boxes, and also to any of the four panelists. So let's see here. We have a question for all speakers. I am a professor at the Federal Rural University of Pernambuco and would like to know if any of you have worked with reanalysis data to estimate ET. Okay, so I guess I will answer that question. The answer is yes. I did a study here in the US with a PhD student working with me, Clay Lewis, and it resulted in a paper where we examined the use of reanalysis data and climate data to estimate reference evapotranspiration using the Penman-Monteith equation, for example. So that paper is available in the literature, and there's similar studies now along those lines. And if you send me an email, I will send you that copy of that paper. There's a comment by Eusebio Fraga. Great, Jessica, good results and good presentation. So it's more of a comment than a question. Let me look at the question and answer. If there's anything else, any other questions, please put your questions in the chat and we will, for any of the four presenters. Going back to, oops, I think we have another question. So there's a question from Otávio Lagos to me. Can you please extend more of your explanation about the pi dysalexy? Saludos from Chile. Okay, so the pi dysalexy is an open source software that is programmed the dysalexy model, and the dysalexy model is essentially the disaggregation of alexy. So there's papers in the literature from Martha Anderson and others that explain the dysalexy model and how it works. Basically, what you're doing is you are using the alexy, right? You're using the alexy ET at 375 meters. Remember, this is the VERS satellite. So you have 375 meter pixels. You're using that alexi ET as the upper boundary, okay? So then you're using a Landsat imagery at 30 meters that also has thermal IR, and you're estimating the ET that, and what you do is the sum of all the 30 meter pixels, right, have to be compatible with the alexi ET at 375 meters, right? So there's a downscaling and an upscaling scheme in PIDA's Alexi. And then remember, Landsat only, you have an image every 14 days if you have no clouds. And then you have to do the interpolation in between those 14 days. But remember, you have daily values of Alexi, right? And you have 14-day values of Landsat, right? So there's an interpolation scheme using, so in other words, you're using the temporal resolution of the VERS Alexi product and the spatial resolution of the Landsat project. So that's the answer to the question. Let's see if there's anything else in there. That was a question from Otavio. Are there any, Ricardo, are there any other questions that you have that you could see?
No, Christopher, but I'd like to ask you about how is the program in Water for Food Institute to receive students? I'm asking this because we have a lot of students here, and then maybe you can talk a little bit about it.
Sure. So
thank you.
We do receive many students. Jessica is an example of this, right? We've had many students from Brazil that have come either typically on scholarships from CAPES or CNPq, right? In the Sanduíche PhD sandwich program, right? And they typically come for 6 months. And so what we provide is if they have the funding through those programs, what we provide then is we do everything to get the J1 visa paperwork, right? And so as long, and then we provide all the access to the university facilities, to the Water for Food, and to the library, to the computer systems. We provide a computer. And so that's how it works. And so if the student has funding either through CAPES or CNPq or through FAPESP or through some other foundation, and their PhD research is something that we can help them with, right? Something that makes sense that, for example, either working with me or with some other professor at UNL, right now we have a student that just left. He was through the Water for Food Institute, but he was working with groundwater modeling with 2 other professors, right? So there's other possibilities, but we will facilitate bringing them here through the visa process if they have the funding.
Okay, thank you, Christopher. We have no questions in the chat anymore. And then Inovagri thanks everyone that participating here. Congratulations for your presentations, everyone. Jessica, Ivo, George, welcome to Inovagri. It was really, really great having you here participating with us. Christopher, thanks so much one more time here participating with us in Inovagri. Thank you so much.
Thank you, Ricardo, and thank you, Inovagri, for this opportunity for us to organize and present this session. Thank you.
Thank you so much.
Thank you.
Thank you. Thank you.